Hi, this is Shelly, and this is my YouTube channel, AI Economics. I'm a professor of artificial intelligence, and I teach business management students AI concepts decoded for a business lens. If you're interested in this kind of content, please do consider subscribing. Now to today's video. This is part of a sequence of videos which I am developing on developing generative AI models for business managers. It need not be business managers. It could be anybody who is basically from a non-technical audience. What is the motivation for this? The motivation for this arose from the fact that I went through a lot of the YouTube videos which are currently available. And I realized that most of them, though they promised to the development of a generative AI application quickly, actually presupposed a lot of information on AI, which was sort of presumed to be known. So, if you're a person coming in with, say, some minimal knowledge of Python, you might find yourselves very, very confused, even if you follow along on the videos. So, hence, I started this sequence of videos where I begin at the beginning, literally with what is a large language model. And I overview the concepts that I think are required to be known at a very high level. And as I proceed, we'll get deeper and deeper into them and towards the end, we will be having the code tutorials. Now, today's video is part of a subsequence on word embeddings or word vectors and how vectors can actually be represented as words. In my previous videos, I discussed how this was possible and how indeed word vectors follow the relationships between words can actually be made to follow the logic of and can actually be represented by the logic of vector operations, which is very, very fascinating. In today's video, I'm going to be talking about how we can determine whether two words are similar or not. A very popular concept which is used is cosine similarity. Now, I can just see you getting a little terrified by the trigonometric oriented name of this concept. However, it is, first of all, in any case, not that scary. And secondly, the intuition is certainly not that scary. So in this video, I am only going to be presenting to you the intuition and not the maths. So let's see you in this. So let's get going. So what is the core problem solved by cosine similarity? In many tasks, we need to determine how similar two entities are, typically words. So the question that arises is, how do we measure the similarity between words or objects or data? And how can we figure out whether two words are related in meaning or two customers are behaving similarly, etc.? So this schematic below shows that we have three dimensions. I won't specify what they are. And there are three word vectors. And our challenge now is how do we determine which of these words are closer to each other and which ones are closer in meaning or in some sense usage than other words. So that is basically the requirement that needs to be determined by cosine similarity. To understand this concept of similarity, we need to go back a little bit to understand and reviewing the concepts of vectors. Now, vectors are basically powerful tools for summarizing a complex and multidimensional data. This essentially means that an object or a word is measured in multiple thousands of dimensions, and a vector really is a way of summarizing the overall sort of net effect of all these multiple dimensions. All right. Now, the vectors has two features. One is the magnitude or the overall size or strength of the combined effects. And the other one is direction, which is the summary or net orientation based on the contributions from each dimension. The more a vector aligns to a particular dimension, the higher is that dimension's contribution to that vector. All right, now let's try and understand this a little more practically with an example. Now we let's go back to the king and queen example, and we have three dimensions. We have royalty on the x, power on the y, and masculinity on the z axis. Now the word king is supposed to would have a vector such as this, which is 8, 6, and 2. That means king is doing very well on the royalty axis because obviously the kings are royal, hence the number 8. It is doing a little less well on power because sometimes kings have power and sometimes they don't necessarily, and they're titular heads. So we have given the king has a vector of 6 on the power axis. And I have chosen that if a person is a male, they take a value 2, and if they're female, they take a value 1. So this vector that you can see over here is the net effect of these three individual components. All right? And we can hypothesize that the strongest influence on the king is basically coming from the royalty factor and to some extent the power. Now let's take the case of the queen vector. Now the queen also does very well on royalty, that is 8. However, much less well, maybe due to patriarchy or gender relations on power. So queen only has 4 on power. And lastly, in terms of gender, it is 1. So therefore, the queen vector is a slightly shorter vector and but broadly, as you can see, both king and queen are pointing in roughly the same direction. And a very major reason why they're pointing in the same direction is the fact that both of them have a very strong royalty component which is making the two words very similar. They are differing both or a little bit on power and definitely on gender. So these two components cause them vectors to diverge a little bit, whereas royalty causes them to actually come closer together. So I hope this explains to you how different components or dimensions will actually influence the similarity or dissimilarity between words. Now we come to how do we measure this similarity? There are many challenges for measuring word similarity. The first is that word vectors have many, many dimensions, typically running into thousands, and capturing abstract features like semantics, context, or relationships. So there is no real intuitive way that we can do it. And frankly, there is no simple geometrical or algebraic way. This has to be done in a multidimensional way. Secondly, they also have non-intuitive meanings. Vectors are abstract representations of the word. Therefore, if the numbers that are into a vector are basically don't directly mean that something is happy or sad or masculine or feminine or royal. Instead, they represent relationships that emerge from the training data. So these are the challenges that are there for trying to measure similarity of vectors. How is this being sorted out? Typically, there is a very simple way by which a vector similarity is measured, and that is if you have two word vectors A and B, cosine similarity is defined as the cos theta, that's the cos of the angle, which is defined as A dot B, and this is, I will explain this formula a little bit, divided by the magnitude of A and the magnitude of B. Now A dot B is the dot product of the vectors, which I will explain. A in two square straight lines and B are the magnitude or lengths of the vectors, and theta is the angle between the two vectors. But first, let's understand, what does cosine similarity measure? Now, how does it measure the similarity at all? Now, suppose you have two vectors which are somewhat aligned to each other or similar. You have king and you have queen. You will find that the angle between them, that is theta, is likely to be smaller, in which case the cos theta is closer to 1. This, this effectively means that if the cos theta is closer to 1, it means they are relatively similar vectors. On the other hand, look at this. You have king and you have banana, and they are literally at right angles. Now, if angles are close to 90 degrees, it means the two vectors are essentially orthogonal. That means they're at right angles to each other. That means they have literally got no relationship to each other, in which case the cos or the cos theta or the cosine similarity is 0. Now, if we can also take into account the case where two vectors are pointing in opposite directions. In this case, there are two scenarios. It is possible they have no relationship or that they have opposites relationship. So if the cos theta angle, is closer to 180 degrees, then we would say that cos theta is closer to -1, in which case it represents opposite vectors. So over here we have the words love and we have the opposite hate. And these, as you can see, are opposite. And hence their cosine similarity will be equal to -1. Now, let's very briefly, and I really don't want to plunge into the world of trigonometry, which I'm sure all of you were very happy to leave behind, and even, but let me just explain the point about the dot product and a little more. Now, recall that when I talked about the formula for the cosine similarity, it was basically the dot product of A dot B divided by the magnitude of A and the magnitude of B. Now the dot product, what is the dot product? Now I have here two vectors, A and U. Now essentially the dot product is a way to combine two vectors to get a single number that shows how much they point in the same direction. All right. So what we really want to know is the extent to which A is pointing in the same direction as U. The dot product is basically defined as the projection of A in the direction U. So basically when we say projection, it is essentially the shadow that A casts in the form of the right angle, this distance, which is known as the dot product. So if you have two vectors, then the dot product is essentially estimating this distance, for example. And it essentially represents the extent to which the vector A is pointing in the same direction as the unit vector U. If A and U are pointing in similar directions, then you can imagine A dot U is the length of the shadow of A onto U. So A dot U is basically the length of this shadow. The formula for dot product. Now again, because it's vector algebra, I'm putting down the formula also. It is simply the multiplication of two vectors, that is A1, if you have two vectors A1, A2 and B1, B2, the dot product is simply the first component of A multiplied by the first component of B plus the second component of A multiplied by the second component of B. And if the vectors have more dimensions, you just basically expand it. So it can go all the way to AN, BN. If the vectors point in the same direction, this dot product, the arithmetic product, is a big positive number. If the vectors are perpendicular, the dot product is 0 because they don't align at all. And if they point in the opposite direction, obviously, the dot product is a negative number. And that makes sense because if, for example, the two vectors are perpendicular, then there is absolutely no possibility of there being a shadow of. So if A were, for example, like this, then there is no shadow. The length of the shadow cast by A on this second vector is literally 0. So hence, the longer is the shadow, the more the more similar are the two vectors. Now, just one further point, if we go back to the earlier dot product, the cosine similarity formula, what we were doing is we have already calculated the dot product. Now we are dividing it by the length of A and the length of B. Now, similarity depends. So, why do we do this? We do this because magnitude can be a bit misleading. If two vectors are of very different sizes and their dot products might be very large or small just because of the size factor, but not necessarily because they are directionally similar. And we want to focus on the directional aspect. So to avoid that, what we do is we normalize the dot product by the two lengths. And by normalizing the magnitudes, cosine similarity ensures that only the pattern of proportionality between components contributes to the similar scores. Geometrically, finally, we can say cosine similarity, vectors that are closely aligned, that is, have a small angle between them, then represent words which are more contextually similar. Vectors that diverge, have a large angle between them, may be opposites or may actually be completely unrelated. Therefore, cosine similarity measures the alignment between the vectors. Well, I mean, this was a slightly heavier lecture video than the usual ones. But I hope I managed to explain to you the intuition behind the cosine similarity concept. This is an important concept in natural language processing, and that is the reason why I did venture a little bit into the mathematical formulas. If you like this video, please do consider subscribing to my channel and also give it a thumbs up. See you in the next video.